Let's talk about the structure of the Earth. So, the Earth is basically divided into four main layers, and they have to do with the state of matter in those layers as well as the chemical composition. So the layers of the Earth, in the simplest form, is the outer surface of it. And think of it as thin on the Earth as the skin of an apple is on an apple. There's this very thin layer we call the crust. Below that, we have a very large region which makes up the majority of the volume of the Earth is referred to as the mantle. And then below the mantle, we have a region we call the outer core. And then in the inside, we have an inner core. And just to keep in mind that it's hot down there. As we go deeper in the Earth, it gets hot. The inside of the Earth is actually quite hot. It's actually hotter, believe it or not, than the surface of the sun. Now, the interior of the sun is quite hot, like 10 million degrees. But the surface of the sun and the inner core of the Earth are fairly similar in terms of, so it'd be kind of looking at the core, would be kind of like looking at the sun. Weird to think about. Okay, so I guess we're going to go from the inside out here. I forgot how I put this together. So the inner core is made of solid iron and nickel. It is rotating quite quickly, and it is about the size of Earth's moon. So it's this fairly large, metallic, solid ball in the center of the Earth that's spinning very rapidly. It, like I said, is 6,000 degrees, which is really hot. Okay, quite hot. Um, Now, why is it hot down there? Well, the main reason it's hot down there has to do with the fact that there are heavy isotopes that are decaying. If you recall from your chemistry class, you probably talked about a thing called the band of stability. As you get larger and larger elements, more and more protons, you reach a breaking point. So once you try to put more than 84 protons together in a nucleus, that's polonium, uh, then not plutonium, but polonium. Once you get above that, there's just no stable configuration. All the neutrons in the world can't hold together, and it'll slowly break down over time in a process known as radioactive decay, giving off usually alpha particles or beta particles, and then releasing heat. And so that the heat of radioactive decay is what makes the interior of the Earth so hot. Now, the outer core of the Earth is interesting because for two reasons. It's chemically almost identical to the inner core, but because the pressure is less, is able to be in a liquid state. The inner core is solid because of the high pressures, but the outer core is, I don't know if you remember phase diagrams from chemistry, but the outer core is liquid, but it's made also of iron and nickel. But because you have the exterior of the Earth spinning at one speed and the core spinning at another one, you get these vortices that form, these swirls in this material. Now, this is very hot metallic substance, and the spinning of that produces the magnetic fields that protect Earth from cosmic radiation. So the Earth's magnetism is the result of these swirling vortices in this liquid outer core. Now, the mantle is something we really need to focus in on because it's very important in understanding the next concept we're going to be talking about, which is called plate tectonics. So the mantle comprises like 84% of the Earth's volume, and it has, in addition to iron, like the inner core, it also has magnesium, and most especially, it has silicate, which is silicon dioxide. And silicon dioxide is something we associate with the crust, but it's quite a bit of it in the mantle as well. Now here's the thing about the mantle. Again, the pressure changes, and what we find is that we have much of the mantle behaves very much like a slow moving, like cement is capable of flowing, but not very quickly, like almost solidified cement, so or like gum or something like that. It moves kind of slowly over time, but it is capable of motion. So we have the movement of material inside it, which we'll talk in our next movement. But it's very important to understand, just as the core spins and the outer core has these vortices, there is movement associated with the mantle, and that movement tends to be what we call convection currents, the upward movement of hot mantle material and the downward movement of cold mantle material. And that's important because it's going to have an effect on the top layer of the Earth, which is known as the crust. Now, this the upper part of the mantle and the outer part of the Earth known as the crust collectively are referred to as the lithosphere. Litho means rock. And so these are the parts of the Earth, the crust, which is chemically different from the mantle, and the upper mantle behave like rocks you would expect to. They are they break. They are solid. You can hit them with a hammer. I don't know if we really have to pay too much attention to the chemical composition here, but it's worth noting that there's quite a bit of silicon and oxygen present in crustal material, unlike the interior parts of the Earth. So the most common components are silicon and oxygen, most in the form of silicate or SiO2. Now, the crust, as I said, is a very thin layer on the outside, is where you and I live. It's what we think of when we think of the Earth, and it's mostly solid, except in the case of volcanoes. Now, when you look at Earth from space, you notice there are continents and there are oceans. Well, it turns out that the crust is different there. So, continental crust tends to be higher in silicon and oxygen in silicate, and it tends to be considerably thicker. So, continental crust is considerably thicker. Oceanic crust is much thinner. It's higher in iron, higher in magnesium, and lower in silicate. So, it's chemically different from the crust. In fact, the ocean crust is fairly similar to that of the mantle, with a little bit more SiO2 thrown in there. Now, the upper part of the mantle is shown here from a depth of about 10 kilometers to 100 kilometers. The upper mantle, known as the lithosphere, and the continental crust, we refer to as the lithosphere. Now, all this business about the inside of the Earth, how do we know this? It turns out no one's ever been there. I mean, we build mines, we dig mines into the Earth, but the truth is, uh, no one's ever going to get down there. Now, we don't know what the interior of the Earth is because we've drilled. The deepest hole we ever drilled was about 12 kilometers deep, and they had to stop drilling because things melted. The temperature was up to 180 C. So it definitely gets hot down there. We know that. When we think about volcanoes, it's definitely hot in there. Well, then how do we know what the interior is? Well, it turns out the way we know, primarily, apart from the Earth's mass, is also from looking at earthquake data. So let's just talk about earthquakes a bit here. Uh, Earthquakes basically are sudden movements of the lithosphere that occur along breaks in the lithosphere, primarily the crust, but also the upper mantle. Uh, and we refer to these breaks as faults. So a fault, as you see, here is a fault here, here is a fault here, here is a fault here going sideways. These faults are just breaks in rock along which motion has occurred, and they come in four types. So basically, what happens is three types. Forces build up along these faults over time, and depending on the type of force we have, is what type of fault we get. But basically, force builds up over time along these faults. But the faults they're solid, so they're stuck in place. They don't move. So imagine yourself pushing on a heavy box, really heavy box. You push, it doesn't move, and eventually it moves really fast. That's an earthquake. All this pressure builds up, and all of a sudden, that's an earthquake. Now, there's three different types of forces that we're going to get. There's gravity, in which case one part of this side of the fault wants to fall downwards, so it tends to extend the crust a little bit. So there's gravity is one of the forces. It tends to cause divergence, separation of the Earth's crust. We have compression, which is when internal forces of the Earth, that we'll talk about in our next lesson, push the crust together. So we get compression. Also, it pops up. We call that a reverse fault. And then we get shear forces, where two pieces of crust are trying to push past each other, and they suddenly slide horizontally past each other. We call that a strike-slip fault. I don't think you will need to know the names of the faults. I wouldn't focus on the names of the faults. I just wanted to make the point of there are different types of forces involved, but in every case, energy builds up in these faults over time because of the buildup of pressure. So eventually, what happens is this pressure is too great, and it releases all of a sudden, and that sudden release of energy, like I said, like when you push on a box and it suddenly gives way, that release of pressure releases energy, and that energy is released in what we call seismic waves. Very similar, some of them to sound waves or water waves, both of which are, waves are a way of energy manifesting itself, and so these are called seismic waves, I mean just within the Earth. Now, these waves will move away, like if you've thrown a rock into a smooth pond surface, you've probably watched the ripples move away. Same analogy. The only difference is there's more than one kind of these waves we'll talk about in a minute. But there's a point along the along the fault where the movement actually occurred, and we call that the focus of the earthquake. That is where the energy was released, and it released a lot of energy. It's like an atomic bomb at times. Okay, that much energy, more. So we release energy at one point, and then these waves carry that energy across the earth, and the earth just rings like a bell afterwards. These waves go back and forth across the earth, and we can register these waves with a device known as a seismograph. Uh, Now, you may have to know for the test the terms focused and epicenter. The epicenter is the point on the surface directly above the focus. And so, as far as the surface goes, that seems like where the earthquake started, even though it actually occurred deeper inside the earth. So earthquakes produce two different types of waves, and this is going to be important in order to understand how it is that we know what the interior of the Earth is. So the two different types of waves that are produced are called P waves, which is also known as primary waves. They're the first ones to arrive; they're the fastest ones, and they're analogous to sound waves. Uh, think P is push and pull. So they cause a back and forth motion of rock material, and is essentially equivalent to a sound wave. So you have regions where the material is pressed closer together, which we call compressions. This diagram is calling it a dilation. We usually call it a rarefaction, but the point is, here's where the rock material is a little bit farther apart, so that you have slightly higher density, slightly lower density. Same thing's happening with what I'm talking right now. I'm making the air slightly denser, slightly less dense by pushing it back and forth. It's identical to a sound wave. S waves, on the other hand, are known as shear waves or secondary waves because they arrive second because they're not as fast as the P waves, and they involve like a side to side motion. All right, what we would call in physics a a transverse wave. Good brain fart. Okay, so this is what we call a longitudinal wave, and this is what we call a transverse wave. Not that you need to know that, but maybe you've taken physics and you could remember. But basically, it's like shaking a rope like this. Okay, so it's moving like this. Okay, uh, and the thing about these S waves is you can make sound waves, you can make P waves, sound waves go through liquids. You can't make a wave like this move through the interior of water. If I take water and lift it up, it doesn't make the rest of the water go like this. Okay, don't think about surface waves. There's also, just like the surface of water can have waves, the surface of the earth can have waves, but we're not going to go there. That's a little bit too much detail. But the point is, the thing is, P waves can go through both solids and liquids. S waves can only go through solids and not liquids. And that's how we know what the inside of the earth looks like, because every time there's an earthquake, here's my epicenter, my focus rather, and those waves go moving out and they refract or bend as they travel because there's changes in density. Again, we don't have to get into details of that, but that's why they're bending. And what we find is this: S waves, shear waves, secondary waves, they're the ones that cannot go through liquids. And what we find is there's a shadow zone on the earth all the way from here over to here. So there's this, when an earthquake happens here, only this part of the world will register the S waves. The rest of it will be silence in terms of S waves. They just don't arrive. And the only explanation is there must be liquid. And in fact, by taking the angle here, we can figure out how deep that liquid zone must be. Now, why do we think there's a solid inside that liquid? I'm glad you asked. Yeah, two things. One is the main thing is that we can tell by the way that the P waves move through, because P waves move faster through solids than they do through liquids. So if we look at how long it would take a P wave to travel through a solid, it would arrive at one time. We said, okay, well, it's not solid. There's this big liquid in the middle. Well, it would arrive a bit later because of that. So we could calculate how long that would be. Let's just say it would arrive here. Let's just make up a number. 15 seconds later. Okay. So it would take 15 seconds to travel through the earth and arrive here. But what happens is it arrives in less time than that. And so we can look at that shortening of time and infer that there must be solid in the middle, and we can use precise measurements of those arrival times and say, okay, the interior solid part of the world must be this big. So that's how we know what the interior of the Earth looks like. Okay, so again, we have the crust, the mantle, the outer core, the inner core, and the main things that you need to know for this unit are the crust and the mantle. Those are the ones that are going to be important in a concept we're studying next, which is called plate tectonics.